Yeah, thanks for the introduction. Hi everyone. Today I'm going to talk about a work on building Abelian high-dimensional expanders. This is based on joint work with Yotam, Dikstein, and Wigderson. Okay, let's jump right in. I guess since Rachel already talked a little bit about complexes, so hopefully this is not a scary word anymore. So yeah. Okay, but let's start from the more familiar object of expanders. So we all know expanders are a type of graph where random walk on it mixes fast. And throughout this talk, I will talk about lambda expanders, which are expanders whose second eigenvalue is upper bounded by some constant lambda that's bounded away from 1. Okay, this measures how good the expanders are. And we know like expander has many applications in computer science, especially in complexity, including like it played roles in de-randomization, construction of condensers and extractors, and also like appeared a lot in hardness reductions and building hard instance, explicit hard instances for many questions, and also the construction of error correcting codes. So it's a very important object, as we all know. And since it has been studied for like decades, we all know like a lot of constructions of expanders. So in particular, we know that from Pinsker that most random D-regular graphs are expanders. So that's very nice, they're abundant. And later in the 70s and 80s, a bunch of people in the math community told us like there are many algebraic constructions of expanders. These are based on results in number theory, and they construct expanders that are locally tree-like. So you don't see many short cycles in such expanders. And then after that, in the 20s, early 2000s, or not 20s, in the early 2000s, we start to see like more combinatorial constructions of expanders based on combining techniques of combining smaller expanders into bigger expanders. And these expanders looks a bit different. They would include short cycles, but these really expands the way of like constructing expanders for us. So this is the story for expanders. Now I want to move to high-dimensional expanders. So high-dimensional expanders, roughly speaking, is generalizing the spectral expansion in expanders to higher dimensional graphs, which are actually complexes. I give a very intuitive definition on the slides, which is saying like, okay, essentially a high-dimensional local spectral expander, which is the object we'll be focusing on. It's actually a connected high-dimensional graph whose local neighborhoods are all expanders. I'll explain more about what this exactly means later. But just to say, like, despite the fact that these objects haven't been studied for that many years in the computer science community, we already have very cool applications of it, including in the sampling application in resolving the Mihail-Vazirani conjecture of sampling spanning trees. And also, as Rachel mentioned, it also played roles in like building really good locally testable codes and quantum low density parity check codes. And it also has applications in hardness of approximation in constructing explicit hard instance for resolution proof system, for example, for like KXOR problem. And also in the more recent work in proving parameters of PCP theorem. Okay, so, but I guess to this audience, I want to say like, I think there are many potentials of high-dimensional expanders, using it in place of where expanders used to appear in these applications and potentially improve a lot of the results. So that would be a very interesting application direction. But I guess my talk today will be mostly focusing on the construction side of high-dimensional expander. So to talk about constructions, maybe I will first explain what actually precisely is a high-dimensional expander. So the definition I'll be using is this one called local spectral expansion. So the definition is that a k-dimensional local spectral expander is a connected k-dimensional complex whose local neighborhoods are all expanders. So a k-dimensional complex, essentially, let's think about it as a uniform k+1 hypergraph. So it's defined by some vertex set V and also a set of order k+1 hyperedges we denote x of k. And also all the subedges contained in these order k+1 hyperedges. So I'll call these sub edges like x1 through xk-1. So there is a off by 1 indexing because of historical reasons, but just to say that we in general don't, in this talk, we'll be focusing on the case of k equal to 2. So we'll be thinking about two-dimensional complex. So exactly like what Rachel was saying, like these are complexes where you should think about them just as graphs, but adding some additional triangles to it. Okay. So here's an example, like 4 or 5 vertices, a bunch of, okay, you probably couldn't see, but there are 3 triangles here. And also all their sub-edges are contained in the complex. And there's the Hessel diagram of this graph. This is sometimes more straightforward to write. Okay, so next I need to define what is a local neighborhood. So specifically for 2-dimensional complexes, we can define the local neighborhood of a vertex. So a local neighborhood of a vertex is also a graph, and it's a graph whose vertices are all neighbors of this vertex V, and whose edges are edges in the original graph that when union with V forms a triangle in the original graph, in the complex. Okay, so in this example we're showing, if I take V to be this one vertex, then the link of V would actually, or the local neighborhood, or also we call it the link of V, would be consisting of these 3 vertices, which are neighbors of 1, and also these 2 edges, because there are these 2 triangles that's formed by union these 2 edges with the vertex 1. Okay, so it's always the case that the link of a vertex is a subgraph on the original complex. Okay, so just like this is a subgraph on the original complex. So this is how we define local neighborhood. I mean, it's local because it's really only a graph induced on the neighbors of a vertex. So it's local. And now with that, we can talk about what is formally a 2-dimensional expander. So we say that a 2-dimensional complex is a 2-dimensional lambda local spectral expander if it's connected as a graph. Okay, so first it's connected as a graph, and secondly, we need all the vertex links to be lambda expanders. So if we take every vertex and look at its link, its local neighborhood, we need that to be a good expander. I guess this is just a very simple example of a tetrahedra, so or a fork-clique, where we have like 4 triangles and 4 vertices. This is a 1/2 expander because first because it's connected as a graph, and second, if we look at the vertex links, all the vertices vertex link is just a triangle. Okay. So this is a very simple example of high-dimensional, 2-dimensional 1/2 local spectral expander. Okay, so now we want to summarize like what we already know about the construction of high-dimensional expanders. We know much less when compared to what we know for the expander case. In particular, we said expanders like random deregular graphs are expanders. So if we want to ask, okay, do we have like nice random models for like high-dimensional expander? The answer is no if we insist on having like a very sparse high-dimensional expander. Here, sparsity, I mean like each vertex is contained in a bounded number of hyperedges. So it turns out, for example, if I'm still wanting to take random deregular graphs, and then I construct a 2-dimensional complex from it by adding every triangle as a order 3 hyperedge. So if I do it that way, I will realize that actually, if now I look at the vertex links, it's just a subgraph induced by the neighbors of a particular vertex V in the original graph. So this graph wouldn't be connected with high probability unless D is much bigger than square root n. So in this sense, we don't have a very sparse high-dimensional expander, sparse random high-dimensional expander. So that's the first difference from in comparison to expanders. But luckily, some of the other constructions of expanders generalize. Those are the algebraic constructions. So there are a bunch of like works in the math community about generalizing those constructions of like algebraic constructions of, for example, like the Ramanujan graphs and stuff, and also like the coset geometry type of construction of expanders into the world of high-dimensional expanders. So these kind of construction actually would give us a would give us bounded degree arbitrarily good local spectral expander. So it can achieve degree that's depending only on the dimension of the high dimensional expander and the lambda, but doesn't depend on the number of vertices in the graph. So it's pretty good. That's kind of the summary so far. But okay, but there are something unsatisfying about this answer. I think the first objection is that, okay, these uses very deep results in number theory. So for most people, including myself, I don't have much intuition as to why this specific construction, like this specific choice of groups, this specific choice of quotients will actually give me high dimensional expansion. And secondly, because of using the group structure, what happens is that imposes like very rigid constraints on what kind of vertex degree you can pick and what type of links can appear in these kind of constructions. So a very very natural open question here is to find less restrictive and more intuitive constructions of high dimensional expander that are also have like bounded degree ideally. So that will be the question we'll be tackling in this in the rest of this talk. Okay, but well, the short answer is we don't get a bounded degree high dimensional expander. The best we get from these kind of more intuitive elementary construction is like subpolynomial degree. But yeah, let me just first talk about that result. And in the open question session, I will say some directions of how we might tackle this problem eventually. Okay. So actually, before that, any questions so far? Okay, so to explain the construction, let me first start by introducing metric space and geometric graphs. And from there, we'll get some intuition about why the construction we have eventually will be a high dimensional expander. So recall that a metric space is parameterized by a set and a distance function that specify distance between pairs of points in the set. Okay, it could be a metric space, could be continuous or discrete. And the geometric graph over a metric space, which I denote by GM, uncommon tau, is given by basically a geometric graph over a metric space M is specified by n points on this geometric in this metric space, and a bunch of edges which connects points. Connect these points as long as their distance is at most tau in this metric space. So as long as you can find this kind of set and define this like this adjacency matrix, then this graph can be viewed as a geometric graph over this metric space. Okay, so the nice thing about this geometric graph is it inherits some geometry from the underlying metric space. So you can imagine like this geometric graph when placed, for example, nicely, for example, like if I just sample randomly the endpoints, then in some sense it's a random discretization of the metric space itself, or a random like a random smaller version of the metric space itself. So this is how we think about these geometric graphs. So why would this geometric graphs be good for constructing high dimensional expander? Well, the intuition comes when we compare it with a random deregular graph. So let's consider a random deregular graph and a random geometric graph over some metric space in which we pick the distance tau so that the average degree of the graph, for example, is also just equal to D. Okay, so we compare these two types of graph, roughly have the same degree. And we think about how, like what the link in the two graphs would look like. Here by link, I really just mean I take a vertex and look at the subgraph induced over its neighbors. So I mean, that's a straightforward way of like, of converting a graph into a two-dimensional complex and then look at its link. That would be precisely the structure we're looking at. So if we're doing that, if we're looking at the link of a vertex V over here, in the random deregular case, we'll have some probability of say like a vertex of neighbors U and W, we'll have some probability of them being connected, which is roughly like D over N. Okay, so that's just roughly the marginal probability of an edge exists between U and W. However, if actually I tell you that this graph is a random geometric graph, which means that like we know that both the point correspond to U and the point correspond to W. They're close to the point correspond to V. So if we pick the threshold tau close enough, it kind of by triangulating equality, we know that U and W have to be like 2 points that are within 2 tau from each other. And if I'm in my random model, which means like U and W are sampled randomly, and conditioned on knowing that they're close, like they're 2 tau close, they have like there's higher probability than d over n of them being connected in this random geometric graph. And because of that, I can imagine the link of a vertex to be denser because the marginal probability of an edge is higher. So that's kind of why we would expect a geometric graph to behave nicer than just a deregular graph when forming high-dimensional expanders. Is this intuition clear? Okay, great. So then what we did is to pick our almost like the most familiar metric space for us, which is like the metric space of over like hypercubes with Hamming distance. Okay, so if we think about this metric space, and we construct the geometric graphs over this metric space, and we want to test whether that would be a high-dimensional expander or not. So specifically, we pick the vertices in this geometric graph to be the all even weight strings in my hypercube. And we pick which we connect the 2 strings if their Hamming distance is equal to d times p. Here, maybe you notice that there's a slight difference. Like previously, when I say geometric graph, I said, okay, I connect things as long as their distance is smaller than some threshold. Here, I'm picking equal to, but I feel all the intuition still holds because we know the concentration. Like if I think about it, like all strings that's close to a specific string Si, mostly like is d times p close to a specific string Si, mostly have like distance exactly d times p from the string. So it's just a simplification, and this simplification is because of this simplification, actually we get some benefit in analysis, which we'll see later. So now we get a graph, and this graph is a connected Abelian Cayley graph. Maybe one thing I should say, if you're quick in thinking about it, I'm specifically only considering parameters d times p that are even. So all the even Hamming weight strings can be connected to each other in that way. So we get a connected Abelian Cayley graph. Abelian Cayley graph because the underlying group is 0, 1, the even strings in 0, 1 to the d. That's an Abelian group, closed-ender addition. And we have a bunch of generators, which are essentially all the strings of weight d times p in this group. And because of that, we can alternatively view this as a connected Abelian Cayley graph. So this is the graph, and now we add the 2-dimensional structure onto it by simply taking all the triangles in this geometric graph and add it as the order 3 hyper edge in my construction. Okay, so this would be the Abelian complex that I'm referring to in the title. Okay, so now we get a construction, and that's connected. So the next thing we need to analyze is just its vertex links. If it's a good expander, then we can conclude that this is actually a high-dimensional expander, right? It's not hard to see what a link of a vertex is. Also by symmetry, it's enough that I'm just looking at the link of the all 0 string, okay? So if I look at link the all 0 string, first in its link, all the vertices are simply just like weight d times p strings in my hypercube. So for example, S1, S2, S3. And also I'm looking at the induced subgraph over them, which means like 2 points Si and Sj are connected if their Hamming distance is d times p. So if I abuse my notation a bit and just use Si to denote the set of non-zero coordinates in my string, then I can conclude that 2 sets are connected to each other if they intersect in dp over 2 points. Okay, and because of that, maybe some of you already realize I'm precisely describing a Johnson graph. A Johnson graph over like a DP slice where two are connected with if their intersection is dp over 2. Okay, and we showed that, well, we already have knowledge about like, Abelian polynomial describes the eigenspace, like the spectrum of such a polynomial. So we can actually analyze it and show that it's a 1/2 minus p over 2 expander. Okay, and because of that, we actually can show that, okay, the Johnson, we call it a Johnson complex precisely because its links are Johnson graphs. So these Johnson complexes are two-dimensional local spectral expander with this parameter. And in general, there is a way of generalizing it to k dimension, general k dimension, and prove that actually in the k dimensional version is a 1/2 minus p over 2 to the k minus 1 local spectral expander. So the precise number doesn't matter too much, but the main thing maybe you will notice here is that actually we have the constraint that, okay, we can only choose p to be in this range, because if we pick p to be too large, actually our complex will have very high degree. And at that point, there's no difference from just picking a random deregular graph. So here comes the drawback of this construction. In this construction, if we insist on the degree to be like smaller than what a random deregular graph would give us, we cannot get like very good lambda local expansion. In fact, we cannot get any lambda that's smaller than 1/2 minus p, 1/2 minus 1 over 2 to the k. So there's a bound barrier. Because of that, we actually are get inspired by a work by a complex constructed by Golowich, in which he used a slightly different metric space. So the way to describe this construction is that, okay, we're still kind of looking at the hypercube, but now we're treating them as matrices. And now we're looking at a very different distance function in which we measure the distance between two matrices by actually looking at the rank of their difference in over F2. So we can still construct a geometric graph in this way by taking all the 0, 1 matrices and then connect it to two matrices if their rank differences are. Okay, this actually still gives us a Abelian Killy graph. So this is still a Abelian complex. And again, we add two-dimensional structures by adding all triangles as like my order 3 hyperedges. So I guess I don't really have enough time to talk about what the link look like, but the link structure turns out to be really nice. So if I'm looking at a very simple case of like 2x2 matrices with rank difference 1, then if I look at the link is actually a union of 6 cliques. So it's very nice structure. As a result, Golowich is able to prove that actually such a construction give you d-dimensional lambda local spectral expander that first achieve arbitrary lambda, and second, the degree is sub-polynomial. It's like 2 to the square root d, so it's really nice. What we do is we actually generalize this construction to higher order tensors and use a slightly more complicated distance function. And we're able to further reduce the degree to 2 to the d to the epsilon for arbitrarily small epsilon. So this is what we get for local spectral expander. Okay. I guess I don't really have the time to talk about the last result. The last result is on like a slightly different line. So it's essentially, we're looking at a different way of generalizing high dimensional expansion, a different way of generalizing expansion to higher dimension. So this is a totally orthogonal definition of high dimensional expander called co-boundary expander. And we're able to prove that actually the Johnson complex, the first construction, is also a high dimensional expander in this sense. Okay, so I'll just summarize now. So in this talk, I talked about two constructions. The first is the Johnson complex. And the Johnson complex is both a local spectral expander and a co-boundary expander, has small polynomial degree, so not bounded degree at all. And I also talk about a new Abelian complex construction inspired by the Golowich complex, which have improved the subpolynomial degree and can achieve arbitrarily good local spectral expansion. This is subpolynomial, so still far from kind of far from like bounded degree. Okay, so of course, the obvious open question is to actually find elementary constructions where we can improve the degree to bounded degree. But I feel that's a very kind of out there far end goal. So I want to impose two more like specific questions. The first one is about, okay, we know that the classical results tell us like a Abelian Cayley graph cannot be good expanders unless they have log degree. The question is, does such a lower bound or even a larger lower bound exist for Abelian local spectral expanders? So do I have a degree lower bound in which, for which I need at least that degree to achieve like say two-dimensional local spectral expansion? I think the answer is yes, and it should be a degree. I believe it's much bigger than log n. Okay, and the next question is actually about the question I skipped. So I probably couldn't explain it in too much detail, but the idea is like we have like some intuition as to actually why geometric graph is good for constructing local spectral expansion because of the triangle inequality. But there's also some analogous intuition as to why it might be good in constructing these other type of high dimensional expander called co-boundary expander. But there are no formal statement establishing that. So I think that would be an interesting direction because we know even less about how to construct these co-boundary expanders. Okay, so that would be it. Thank you.